So we are given a two-dimensional grid map consisting of ones, which are land cells, and zeros, which are water cells, and we should count the number of islands. This is a classic problem and there is no challenging brute force approach of solving it. But let's solve the example input in order to get a taste of how our algorithm should work. If the grid is full of zeros, there is not going to be any island, that is for sure. So let's start looking for cells equal to 1. We can iterate through the grid, increasingly by rows and columns. When we have found a cell equal to 1, we have just found ourselves a new island. Let's imagine an extra matrix where we keep records of these islands. We will mark the newly found cell as 1 in our example, as it is the first island we have ever found. But that is not enough. We have to make sure that we mark each and every cell of this island with 1. Otherwise, when we find the next cell equal to 1, we will suppose it is part of a different island. So we should discover the whole island before continuing searching for others. We will start from this cell and visit each land neighbor, or, in other words, each neighboring cell that is also equal to 1. In this example, we have found 2 such neighbors and marked them as 1. Now, this is still not enough. Notice there is one more cell in this island which we haven't visited yet, but there could have been many more. So we should continue discovering the island, but this time we will visit the neighbors of the newly found cells. Let's start with the cell on row 0 and column 1 and visit each of its land neighbors. There are 2 of them, cells 0, 0 and 1, 1. And here we have to be very careful. Is there any point of visiting again the cell 0, 0? Not really. In fact, if we do that, we will end up visiting the cell 0, 1 again, because it is the neighbor of 0, 0, then 0, 0 again, and 0, 1 again, and so on and so forth. You can imagine what is going to happen here. Our algorithm will get stuck on these pairs of land neighboring cells and will never end. We surely don't want that to happen, so we should visit each not yet visited land neighbor cell instead. This means that we only visit cell 1, 1 at this point and mark the cell as 1. Then, we continue this discovery from cell 1, 0. It has 2 neighbors, but as we can see in the extra matrix, they are already visited, so there's nothing to do here. Same scenario for cell 1, 1. There are no more not visited cells left from this island, so we can proudly conclude that we have discovered and visited the whole island. This means that it is time to look for another one. Is there any not yet visited cell equal to 1 in this grid? Of course, here it is. Now, we mark this cell as 2 in the island's grid and start discovering the whole island. Because all of its neighboring cells are 0, the discovery of the second island ends pretty quickly. Let's continue looking for another unvisited land cell. We find the cell on row 3 and column 3 and mark it as 3. Then, we visit its only land neighbor, 3, 4, which doesn't have any not yet visited land neighbor, so we have discovered the third island entirely. And because there are no more land cells that are not visited yet, the algorithm terminates. Can you come up with an algorithm to solve this question based on how we have discovered the islands in this input example? Let's come up together with an algorithm to discover these islands. First of all, an obvious observation is that we never visit the cells equal to 0. So let's imagine for a moment they don't exist. We are left with some kind of structure which is definitely not a grid anymore. But what can it be represented by? We have a set of cells, and some of them are connected because they are neighbors. We are basically left with a graph where the nodes are the land cells. But what about the edges? In general, an edge represents a connection between two nodes. In other words, its job is to let us know that we can move from one node to the other. We just have to adapt this definition to our problem. Remember that from each land cell, we have visited each not yet visited land neighbor. We obviously don't know which neighbor is visited or not before beginning the algorithm, but what we know for sure is the pairs of neighboring land cells, and those will be the edges. We will add an edge between each pair of neighboring land cells. The islands of the grid are represented by sets of nodes in this graph. Do you see any connection between an island and its corresponding set of nodes? Each island of the grid corresponds to a connected component of this graph. And the classic algorithm designed to look for connected components in graphs is the depth first search, or as known as the DFS. Discovering the islands of the grid is equivalent to performing DFS on this graph. Actually, this problem is a particular scenario of finding the connected components of some graph where the graph can be represented as a binary grid. Safe to say, you don't need any knowledge about graphs in order to solve this question. You can still use the grid representation and the recursive function similar to the DFS. This approach is known as the fill algorithm. Now, let's take another look at our algorithm and figure out the implementation. First step, we are iterating the grid in the search of cells equal to 1. We will do this by fixing each and every row, let's call it I, between 0 and n-1, and each and every column, let's call it j, between 0 and m-1, making sure that the grid of I and j equals 1. If so, this means that we have found a new island. And finding a new island means that we will increment our answer. Then, discovering the island means that we will call the recursive function, which let's name DFS, with this cell as argument. Using this function, we will visit each unvisited cell or node from the island or connected component. It's your choice how you want to visualize it. After the call terminates, we continue looking for new islands. Remember the infinite loop problem that we have talked about earlier? Let's make sure that doesn't happen and store an extra matrix of booleans called visited, which will initially be populated with only false values. This new matrix is going to be updated while we visit each new cell in the DFS function. Note that you can even mark these cells as visited by directly changing their value in the input grid to 0. Now, let's talk about the DFS function. Inside the function call, we first mark the cell as visited. Then, we will iterate through each and every neighbor, I prime, j prime. There are a total of 4 neighbors, but be careful in case some of them are not valid. For example, when I equals 0, the neighbor I minus 1 and j doesn't exist. So make sure that neighbor's row and column are within the boundaries. For each valid neighbor, which also has not been visited yet, we make sure to expand the discovery process of the island by calling DFS with I prime and j prime as the argument. In this way, each cell of the grid, which is equal to 1, is visited exactly once. So the time complexity of this approach is big O of n crossed m. The memory complexity of this approach depends on the size of the recursion stack and also the extra matrix that we have used. The extra matrix is not a problem because, as we have mentioned earlier, you can mark these cells as visited by directly altering the input grid. But even with that optimization, the memory complexity is still big O of n crossed m. And this is because our approach is recursive and the size of the recursion stack is n crossed m in the worst case scenario.